All right, today we're diving into something pretty wild, a framework with a massive ambition to basically create a shared language for, well, for almost everything. What if you could use the exact same logic from military strategy to understand market economics, or even the laws of physics? Yeah, let's get into it.
So here's a question for you. It kind of sounds like the setup to a really nerdy joke, right? What does the art of war have in common with thermodynamics? You're probably waiting for a punchline, but it turns out the answer is way more profound than you might think.
It's this. Both of them, and a ton of other systems, seem to operate on a kind of hidden universal grammar, a shared logic. And if we can actually crack that code, we could translate ideas from one field, say economics, and apply them directly to another, like physics. It's a game changer. You know how our knowledge gets stuck in these little boxes, right? Physics has its own language, economics has its own, and they almost never talk to each other. Well, this is where the PORE framework steps in. It's trying to be a kind of Rosetta Stone for ideas, a universal translator that lets us see the connections between these worlds that seem totally separate.
Okay, but let's be super clear about something. PORE is not trying to be some grand theory of everything. It's way more practical than that. Think of it more like a shared dashboard, a common interface for looking at and tinkering with all sorts of different systems, from how your company's team works to how an AI agent learns.
All right, so how on earth does this universal translator actually work? Well, this is the cool part. It takes any complex system you can think of and boils it down to just three core variables. That's it. It's a surprisingly simple and honestly elegant way to wrap your head around some really complex stuff. First up, we have rho, but let's just call it the stock. It's pretty simple. It's the amount of stuff in a system. That stuff could be water in a basin, capital in a company, or even something abstract like the morale of an army. It's just what you've got. Next, there's gamma, or the lock-in. This is all about how tightly the system holds onto its stock. You can think of it like the strength of the container holding the stuff. Is it a steel box or a leaky bucket? A system with a high lock-in is super stable and really resistant to change. And finally, we've got tau, which is the system's rhythm. This is its natural heartbeat, its timescale. How quickly does it bounce back after being pushed? Is the system kind of jittery and fast, or is it slow, steady, and methodical? That's its rhythm. And this is where PORE really shows its teeth. See, this isn't just about making some vague, loose analogies. The whole framework demands discipline. You map systems with more and more rigor. You can start with a weak comparison, sure, but you can go all the way up to a very strong mapping, where PORE can literally predict new things about that system, stuff the original theory couldn't even see coming. Okay, so we have this common language now. Stock, lock-in, and rhythm. Cool. But what's the big deal? What's the payoff? Well, let's dig into how this kind of translation could totally change fields from education and engineering all the way to the future of AI. For anyone in school, PORE could be like a meta-curriculum. Instead of trying to memorize a dozen different frameworks as just isolated trivia, you learn this one, stable scaffold. And once you have that, you can transfer your intuition. Suddenly, something you learned about thermodynamics could spark a new insight into how markets work. It connects the dots. For engineers, the benefits are even more direct. I mean, imagine having a single dashboard that could track the health of a supply chain, a piece of software, and a financial portfolio, all using the same exact language. If something's going wrong, you have a clear diagnostic checklist. Is the stock too low? Is the lock-in too weak? Is the rhythm all out of whack? Now, this brings us to what might be the most mind-blowing application, teaching AIs how to think. The details here are pretty intense, but the big idea is this. PORE gives us a structured curriculum for AI. Instead of just throwing raw data at a model and hoping for the best, we can teach it to see the world in terms of stock, lock-in, and rhythm. This could give it a genuine, abstract understanding of how things work, letting it make way better predictions and decisions. But, with any powerful idea, we gotta pump the brakes a little. It's really important to understand the limits here. This is not some magic bullet that unlocks all the secrets of the universe. It's a tool. And like any good tool, it has a very specific purpose and a clear set of rules for how to use it. So it's absolutely crucial to get what PORE is and what it isn't. It's not the one true theory. It's more like a compiler for theories. It's not a magic shortcut. It's a disciplined interface. And most importantly, it's not just a universal metaphor. It's a falsifiable routine. And that's key. It means its claims can be tested and they can be proven wrong.
That scientific rigor is exactly what makes it so valuable. This quote right here really nails the standard the framework holds itself to. It says the key question isn't, hey, can we map 100 different things with this? No. The real question is, can these mappings preserve enough of the original system's structure to make testable, falsifiable claims about how to actually control it? And that brings up a really fascinating question. Why does this even work in the first place? What is it about certain systems that makes them PORE compatible? As it turns out, there might be a deep, fundamental reason rooted in physics itself. It turns out that all these systems that work well with PORE, they share some basic properties. They tend to be local, meaning what happens to them is mostly influenced by their immediate surroundings, not something happening halfway across the world. They're dissipative or open. They leak energy, kind of like a hot cup of coffee cooling down on your desk. And crucially, they don't have long-term memory. Their future depends on where they are right now, not on something that happened a decade ago. And check out this table. It shows this incredible link. On one side, you've got these deep principles from physics, from something called the generalized least action principle. And on the other, you have Poire's everyday practical language. And they map onto each other almost perfectly. A deep physical property like dissipation is exactly what Poire is measuring when it talks about a system's leakage or openness. It means this practical tool is actually grounded in some really fundamental physics. And this connection, this bridge between the practical tool and deep physics, it leads us to a really grand idea, a full-blown scientific hypothesis about why this universal grammar seems to pop up all over the place. So here's the hypothesis. It's like a recipe. You start with a system that has those basic physical properties we just talked about. It's local, it's open, it doesn't have a long memory. Then you add a few more ingredients. Its internal parts mix together pretty fast, there's a clear separation between fast things and slow things, and you can reliably measure its key features. If you have all that, the hypothesis is that a pure-like description with stock, lock, and rhythm doesn't just become possible, it becomes almost inevitable. Think about what that means. It suggests that PORE isn't just some clever model that we came up with. It might actually be an emergent property of a huge class of complex systems. The grammar isn't something we're forcing onto the world, it's something we're discovering because the systems themselves are already built that way. And that leaves us with one final, really tantalizing thought. If this hypothesis turns out to be true, it means there are fundamental, universal patterns woven into the fabric of our world just waiting for us to find them. We started this by asking what war and thermodynamics have in common. But maybe the real question is, what doesn't?